MDM4U 8.5 repeated sampling and hypothesis testing. In this video, part B, we're going to discuss hypothesis testing. Statisticians use the standard deviation of the sample mean to quantify the reliability of statistical studies and conclusions. Often it is not possible to determine with certainty whether a statement is true or false. However, it is possible to test the strength of the statement based on a sample. This procedure is called hypothesis testing. A hypothesis test is an act in statistics whereby an analyst tests a claim regarding a population parameter, mu, or the population proportion, p. The hypothesis being challenged is called the null hypothesis, denoted H subscript 0, which is a claim about the value of the population parameter, mu, or p. An alternative hypothesis, H subscript 1, sometimes H subscript a, is a claim that the population parameter, mu or p, is greater or less than the value suggested by the null hypothesis, H subscript 0. So, in order to talk about how rare an observation is, we need the definition of the p-value. So the p-value of a sample mean is the probability of obtaining your observed sample results, x bar or p hat, or a more extreme value. So, if this is the claim of the center of that data, so whether it's mean or p, your observation for your sample ends up over here. And the p-value is the likelihood of having that result or more extreme. And we're going to include this endpoint or more extreme, the area underneath the curve. And that will help describe how rare that observation is, the area underneath the curve at that point or more extreme. The significance level, alpha, is the probability threshold for deciding whether an observed result, whether the observed results are rare enough to justify rejecting the null hypothesis. The confidence level is the probability that a measurement or conclusion is correct. The confidence level is equal to 1 minus alpha. So if the significance level is 5, the confidence level is 95. If the significance level is 10, the confidence level is 90. So, think about it this way. If our significance level is 5, let's just say that we had this region here to the right, 5% here, 95% is to the left-hand side. If our p-value is beyond this significance level, so it's over to the right of what we are considering to be perhaps 5% for alpha, the significance level, then we would say that that's a significantly rare result. And then it's likely that the true population mean or population proportion p is further to the right than what is being claimed, so that the distribution might actually be shifted over to the right-hand side, and then we reject the null hypothesis. However, if our p-value is closer to the mean than our rejection region or our significance level, then we're going to accept the null hypothesis because it's not a rare result. We'll see this in the context of some examples. A large candy manufacturer produces chocolate bars with labels stating 45 grams net weight. A company spokesperson claims that the masses are normally distributed with a mean of 45 grams and a standard deviation of 2 grams. A mathematics class decides to check the truth of the 45-gram label. They purchase and weigh 30 bars. The mean mass is 44.5 grams. Is this evidence enough to challenge the company's claim? So 44.5 is less than 45 grams, the claim of the company. Now the claim is going to be our null hypothesis, step 1. Our null hypothesis will always be an equality statement. They're claiming a specific value for the center of the data, the mean. The alternative hypothesis is based on your observations. If you conduct an experiment and you see that, in our case, 44.5 is less than the null hypothesis, so an alternative hypothesis would be that it's less than 45. Now, in order to, if we have a distribution, it's possible to have results that are very rare on both extremes. But we have to say, what are we considering for our observation of this data? what are we going to be considering such a rare result for us to stumble upon that we should reject the claim that this is truly the center of the data? And for the question that we're working on, we're going to use 5%. So that means our rejection region is going to be 5%. If we have an observation that would only by random chance occur 5% of the time, and that's what we observed, we will reject this. However, if this happens to be outside of us, our p-value is greater than 5%, or our observation is within this acceptance region, then we will accept the null hypothesis, and we don't have enough evidence to reject it. So, that being said, conduct an experiment that was done by the class that weighed 30 bars and had a sample mean of 44.5 grams. So, just like our repeated samples, we talked about the sampling distribution. And we're going to use the sampling distribution to talk about how rare our result is with a size of 30. Now we know that our sample mean is going to be similar to, the mean of the sample means. So the mean of the sampling distribution will be similar to the population mean, mu. But the standard deviation of the sample means is going to vary based on the number of items that we select. As we discussed, it's going to cluster closer around the middle when n gets larger and be more dispersed when n is smaller. So the standard deviation of the sample means is given by the standard deviation of the population divided by the square root of n, and we will be using 0.3651 as our standard deviation of the sample means. So the probability that x bar is less than 44.5 is approximated by its z-score value. Notice this is a continuous variable, so no continuity correction is needed. 44.5 minus 45, so the deviation, it's negative 0.5, divided by the standard deviation of the sample means, because we're using the sampling distribution, is negative 1.37. Use a z-score table to determine that that is occurring, that p-value, that observation or more extreme happens 8.53% of the time. So, that being said, this is the decision rule, how it's decided. If p is greater than alpha, meaning that our p-value is, if the rejection region is 5 and our p-value is greater, that means that it's closer to the mean and that we should accept the null hypothesis. And if p-value is less than alpha, we reject the null hypothesis, accept the alternative hypothesis. So again, if our p-value is inside of the rejection region, we will reject. So if it's rare, reject. That's my way of remembering. So therefore, accept the null hypothesis because it wasn't a very rare observation if that is truly the center of the data, or really the population mean. Not enough evidence to reject the claim. Let's take a look at one more example. Drug effectiveness. A drug company tested a new drug on 250 pigs with swine flu. Historically, 20% of pigs contracting swine flu die from the disease. Of the 250 pigs treated with the new drug, 215 recovered. Make a hypothesis test of the drug's effectiveness with a significance level of alpha equals 1%. So, in this case here, this is different than the previous example because the claim is about the population proportion. It's claiming that 20% of pigs contracting swine flu will die from the disease. So, we are going to, first of all, determine this is going to be involving discrete data. It's a binomial probability distribution. It has a set number of trials, 250, and P is consistent, independent, 20% of pigs contracting swine flu die from the disease. So it's a binomial random variable. So in order to test if we can use a continuous standard normal curve to approximate probability for a binomial probability distribution, we have to ensure that NP and NQ are both greater than 5. In this case, they both are. This is the expected number of pigs that will die, and this is the expected number of pigs that will survive in a group of 250. So, mu, the expected number of pigs who will die if 20% is truly the proportion of pigs that will die from swine flu, we would expect that 50 in a group of 250 will die. And the standard deviation is given by this formula, the square root of NPQ, and the standard deviation is equal to 6.32. That's a standard deviation formula specific to binomial probability distributions. Next, set up a null hypothesis and an alternative hypothesis for the value of mu in the normal approximation. So the claim is that the population proportion is 20. And if the drug has no significant effect, it should be equal to 20. If the drug does have some effect, then the proportion of pigs that are dying in our sample should be less than 20. So in our case, we observed, it said 215 recovered out of 250. Subtract 250 minus 215, we get 35 died. Divided by 250 gives us, that's 14% of that population died, which is less than the 20% that are expected to die if they receive no treatment. And the question is that difference likely to be due to our intervention or just statistical fluctuations? And we would have to establish how certain we want to be with alpha, but we'll follow the sequence of questions in the textbook. Which hypothesis corresponds to the drug being effective and explain? If the drug is effective, then the probability of death will be reduced. Therefore, the alternative hypothesis corresponds to the drug being effective. Less than 20%, because our drug is causing less of the pigs to die, hopefully. So conducting a hypothesis test. In our sample, 215 out of 250 recovered, which implies 35 pigs died. So, similar to our textbook, we're going to say probably X is less than or equal to 35. This is determining the p-value of our observation. Now, different than the textbook, as pointed out by a student, we should be doing a continuity correction. We're talking about whole pigs. They either die or they don't, success or failure. So the separate values, either 35 die or 36, this is discrete data when our test is a set number of pigs. So our p-value is less than or equal to our observation. And if we want to be less than or equal to 35, we should take a step 0.5 units to the right to apply a continuity correction. The textbook did not do this and actually results in a different conclusion, but it told us to do this anytime we have discrete data to get a more accurate result, so we're going to stick to that. It's true. So we take a look at the z-score value, 35.5, our particular observation, minus the mean, divided by the standard deviation, negative 2.29. That works out to negative, 0.0110, which is greater than alpha, which is different than what they observed with the textbook, but they didn't use a continuity correction. Our answer is more accurate. Therefore, because we have a p-value with more area than what we consider to be in the rejection region, we're going to accept the null hypothesis and reject the alternative hypothesis. So, can the company claim that the new drug is effective? P-value being greater than the alpha or significance level. Therefore, there's not enough evidence to suggest that the drug has an effect on the recovery rate. So that's a different conclusion than the textbook, but it's a more accurate result, including that continuity correction.